I'm Peter Siddons. I'm a physicist here at the Light Source, and my main efforts these days are devoted to developing advanced new detector systems for signal radiation applications, mainly in the X-ray regime. So what I've got here is a setup for scanning fairly large objects fairly quickly. Typical X-ray fluorescence microprobe instruments operate rather slowly. They measure one little dot on the pixel every second or so. This experiment allows us to integrate the scanning stage and the detector acquisition, so we can have a dwell time of a few milliseconds. That's about 1,000 times faster than typical. And so that means you can really scan a macroscopic object, like a picture, in a couple of hours and get a nice high-resolution image. So this is a collaboration between NSLS and the instrumentation division and an operation called CSIRO in Melbourne, Australia. The guys in Australia have expertise in high-speed data processing and image manipulations, and that jives exactly with our need to swallow the data from a high-speed detector that we developed here. So the collaboration between the two gives us the capability of putting together this integrated instrument that lets us do these really fast scans with high resolution. We imaged some pictures from the San Francisco Fine Arts Museum, where we were interested in what was underneath the paint. It turned out those paintings were painted over a photograph, and we were able to image the photograph without removing the paint, just by using the X-ray fluorescence signature of the silver in the photographic print. And we did that for 2 pictures. And so that made us known to the world in this art history kind of context. So the way this thing works is we make a very small X-ray beam, 1/10 of a millimeter square in this case, and we put the picture in that beam, and we look at the X-rays that are stimulated by the synchrotron beam with our fancy detector. And then we move the picture through that spot in a raster fashion, so we gradually cover the entire picture with these 1/10 of a millimeter square intensity maps. And then we can reconstruct that into the image of the picture based on what elements are in the paint. So we can see where is the iron in some kind of red paint, we can see where the copper is in some kind of green paint, and so on and so on. That lets us really reconstruct the picture. I mean, compared to the usual dry scientific stuff, this is real, got human context in it, and it's really nice. Very, very different from what we normally do here. So we're using this high-tech tool, which was developed really for hardcore science, to tell us something about humanity, which is always nice.